So it's my great pleasure to introduce the first speaker, Katherine Kuchenbecker. Katherine is a professor, is director of the Max Planck Institute for Intelligent Systems in Stuttgart, and also professor at Stuttgart University. And she has earned her PhD in mechanical engineering in Stanford University. She has worked afterwards with Alison Okamura, who is coming next, by the way, and she was also at UPenn. So, Katherine, the floor is yours.
Thank you so much, Raja, for the kind introduction. I'm Katherine Kuchenbecker, and I'm really happy to be here to help celebrate the 40th anniversary of our beloved ICRIC conference. To start, I want to ask how many of you have recently lit a match? Is that something you've done recently? Maybe lighting some candles? I want you to reflect on which of your senses helped you do this everyday task. Now, in this session, we have a lot of computer vision researchers, and I'm guessing vision might be something you're thinking of, and it absolutely helps us. But I want to test that. Do you think I can light a match with my eyes closed? Let's test. Eyes closed, clicker down, find the box. There it is. Okay, open the box. Yes. One can do a simple task like this and light a fire in a public building. We can do tasks like this with our eyes closed. What about the converse? Do you think someone can light a match with numb fingers? I'm going to show you a very famous video from the lab of Roland Johansson. He's one of the most famous early researchers of touch neuroscience. This woman's thumb, index finger, and middle finger have been anesthetized, and she's trying to do the very same task that I just did without my eyes open, with my eyes closed. And you can see she's having a really hard time finding the match, getting control of it, holding it, and even once it's in her fingers, she's really still struggling to control its physical interaction with the world. And I think this video speaks to something that Sang-Bae Kim talked about in his keynote yesterday, that we as humans tend to take for granted the perceptual and motor capabilities that are built in, that we are seldom without, and we have little appreciation for what's more difficult for robots and computers. So yes, we can, and it's impressive that we can do tasks like this without any sense of touch, but clearly something important is missing, and that's because the sense of touch is essential for humans and also animals, and how we control our interactions with the world. And luckily, neuroscientists have studied this for years, and they know that our skin is embedded with mechanoreceptors that are constantly streaming different kinds of signals. Now, we as engineers, we understand, say, force torque sensors, and we might imagine that's how our sense of touch works, but that's not how it works. You have 4 different kinds of mechanoreceptors in the glabrous skin, and 2 of them are particularly dedicated to respond to high-frequency stimuli. You can feel vibrations up to 1,000 hertz, much, much faster than you control your motion. And it's those mechanoreceptors that are useful, that signal very important events when we're manipulating. So for example, this is my favorite paper by Johansson and Flanagan, showing if you pick up an object and set it back down, they teach us that ensembles of mechanoreceptors are responding when we make and break contact with our skin, new contact and the end of contact. And secondly, when we're holding an object, like when we hold this clicker, we go hit something or drag across a texture, we feel these broad bandwidth vibrations that tell us about the contact state of the object, the tool we're holding. And these are critical for controlling our movement, because when we're moving in free space versus in contact with something, we have to move and we have to switch our control mode. So it's very, very important to know about contact. Now, if we now turn our focus of attention to robotics and to engineered systems, we find that robotic systems often ignore the sense of touch. And particularly, I figured out when I was preparing this talk and deciding what to present, that our systems rarely pay attention to making and breaking contact with the skin or high-frequency vibrations. And I mean this on both sides of the coin, both for haptic perception, when we're trying to give robots a sense of touch to interact with the world and with humans, and also in haptic actuation, when we're trying to create haptic feedback, say for a user touching things in virtual reality or remote controlling a robot or using a prosthetic hand. And so this insight really forms the foundation of two quests that my team is pursuing. I lead a department called Haptic Intelligence Department at the Max Planck Institute for Intelligent Systems in Stuttgart, and we are working simultaneously to give robots excellent haptic perception. This means making new tactile sensors and integrating with robots, doing the touch processing, which has to be very fast. If you heard Davide Scaramuzza's talk yesterday, you also heard about event-based. We need to complement low-frequency sensing with high-frequency event-based sensing. And then on the dual side, we also work on giving human users an excellent haptic feedback. And again, this needs to be distributed and multimodal. And in particular, I think there's great utility in working on these two problems in tandem. There are very few labs around the world that work on both sides of these problems. They're kind of like the synthesis and the analysis, or the generation and the perception side of haptics. And I find great utility in working on both. And in both, I have found there's a benefit for looking at this making and breaking contact and vibration transients. And so to help make this more real, I chose 3 projects from my team's work over the years, and we'll just jump right in. The first one is about teleoperation. So when a surgeon sits down to control a Da Vinci or other surgical robot, they normally cannot palpate, and they want to. They want to be able to feel the tissue and find where the cancer is or find where the calcified artery is. And I had the luck of Claudio Pacchirotti. At the time, he was a PhD student with Domenico Pratechizzo. He came and visited my lab at Penn, and we worked together and published a series of papers. And it culminated in this paper where we showed how one could do palpation in robotic surgery. So we took a multimodal tactile sensor that measures pressure, vibration, temperature, and deformation, a BioTac, and attached it to the end of a Da Vinci robot. And then we streamed that data to the user's finger, adapting a device that had been built and designed in Domenico's lab that has a platform. And we also added a vibration actuator. And then I can't tell you how we did it, but we took data and basically had the sensor wear the actuator to figure out the space of sensations we could create. And then in real time, while the operator is palpating, this is a fake tissue, and it's a 1D search test. You have to figure out where is the rod that's embedded, like the calcified artery. And if you watch here, there's, you can see the front of the platform kicks up when you get close to the stiff object. And then when you go past, Claudio's showing, it will kick up at the back. And so you can feel where the gradient of the pressure. And so what we found in this study is that by combining this contact and pressure feedback, this significantly improved how people could do palpation compared to no feedback. They liked the interface much more. And also a subset of our users, instead of poking, they dragged their finger, and for them, the vibrations that showed the transient in the material properties helped them do better, and they liked it even better. So that was the first of these 3 projects. We're going to move from teleoperation to human-robot interaction. This is the doctoral dissertation of my former student, Alexis Block, and we wanted to create a hugging robot that could give a really nice interactive robotic embrace. So she patted it, she put it in soft and warm outfit. And in our first studies, we found that people, when they were hugging the robot, they would often pat it or squeeze it, and they were offended that the robot did not respond. And so for this second big paper in her dissertation, we took more advantage. There was some instrumentation in this inflated, we call it the huggy chest. There's a microphone and a pressure sensor. And so we collected a big data set of what the robot felt in its pressure sensor and its microphone when people held it or patted, squeezed, or rubbed its back. And then we trained a little machine learning classifier that operates on windows of data. And we could get very good accuracy in real time to know what the person was doing. And then when it all comes together, this is a participant in a later study, a validation study, where the robot invites him to come over for a hug. It closes him, it's basically grasping him. It closes until the torque limits are exceeded. And now we have a nice, warm, cozy embrace. And if you watch his hands here, he's going to pat the robot. We see this is the real-time visualization. So he starts patting, the robot rubs him back. And then now the robot's squeezing him. It's hard to put in a video, but now he squeezes. And so there's this conversation, this haptic conversation that's happening between you and the robot. This is another participant. People really enjoy being hugged by this robot, especially they love being squeezed. They found it felt much more natural and enjoyable and intelligent. They always thought it was friendly even before they had hugged it much. And they did a lot of these intra-hug gestures. And the key to its performance was that we could do this real-time perception and taking advantage that we were sensing contact and these high-frequency vibrations through the microphone, and that let us really distinguish what's occurring. Now, we took this robot also to Hamburg for Haptics 2022, and we hugged more than 100 people over the course of several days. This is the third speaker in the session today, and we were really honored to win the prize for Best Demo. So it pays to have good haptic perception. The last project I want to tell you about is much more recent work. I forgot to say, Alexis is continuing to pursue this work now. She's a professor at Case Western, and Claudio, who did this work, he's now a researcher in CNRS. So the last project I want to tell you about is the doctoral dissertation of my PhD student, Natalia Sanchez-Tamayo. And we are working on how can we give good haptic sensations on hairy skin. So your hairy skin covers most of your body, and it's much less sensitive than the skin on your fingertips. So we all have devices like this, and what do? They buzz. That can get our attention, but it gets a little annoying, and it's not appropriate for all kinds of communication. And so we wanted to create a device that's just as compact and usable, but that can also make and break contact with your skin and press, so we can have a much broader, richer vocabulary of haptic sensations in a wearable device. And in the beginning, we didn't really know how to do that. Doing it with servos or electromagnetic motors or pneumatics is challenging. And so we found, luckily, her co-advisor, Christoph Keplinger, previously when he was at University of Colorado Boulder, had co-invented these hazels, these artificial muscles that I think are like miracle actuators. They work so well. Each one, we make little pouches that are filled with oil. They're like a bag of oil with electrodes on the outside. And when you apply a voltage, it might need to be a few thousand volts, then it squeezes together and you get extension. It's very low current. They're basically capacitors. And we put a stack of these 10 pouches. We assemble them together with an elastomeric layer, and we mount it off the skin. And then when we apply the voltage, we can make and break contact with their skin and deliver broad bandwidth vibration transients. This is how it works. When you're looking from the side, you can see when we increase the voltage, we can press on your skin. We can do it gradually. We can play wide vibrations. I'll just watch one more video. You can see we can vibrate really, really well. And we were able to document. We have huge stroke, very high forces, bandwidth up to 200 hertz. And we also did a perceptual study where people had almost perfect accuracy, recognizing 6 different cues. And most importantly, they rated these cues as very pleasant. So we can give a lot of different sensations, and it's silent, and it's quiet, it's very, stays cool, and it's very energy efficient. This was just accepted to advanced science. So those were the 3 projects I wanted to tell you about. They are steps along the way towards the quest that we're pursuing. I know many other people are working on these too. Maybe I've gotten you excited about working on touch as well. With that, I want to thank my current lab, my colleagues at the Max Planck Institute for Intelligent Systems, my research community. I would invite you to come visit us at World Haptics 2025 next July, if you're interested in touch. And thanks to Tamim and all the other organizers and everyone else who has supported our work.
Thank you very much, Katherine. Any questions? If you have questions, please wave your hand because I don't see very well.
Yeah. Hello, Katherine. It was wonderful to hear you, see you. And we miss you in Philadelphia, I can tell you that. But my question is, what is the reason that the development of haptic as such is so slow as opposed to vision, which really gives you just information of the distance? This is much more contact, so.
I think there are several reasons, Rujana, and I know you did really amazing early work in the GRASP lab on such topics, and many other people are. I think it's a very complex mechatronic system. Whether we're talking about sensing or actuation, so many individual units, they have to endure physical contact and stay robust and stay constant. And I think we are just years behind where vision is. We don't even have standards on how do we capture touch. And it's much more, there's a closed loop between motion and sensation, and it's much more diverse. I wasn't even talking here about temperature or pain. So I think we're making steps. It requires an interdisciplinary mindset, which is why we collaborate. I think also machine learning is helping, and material science. So I'm collaborating with material scientists and machine learning experts to try to make big steps forward in touch. I'll be here all week. I would be happy to talk to anyone else if you have questions. Thanks so much.
It's not over.
Oh, it's not over.
Yes, no.
Sorry.
I need people to ask questions, especially young people, students.
I
It's
saw
a
this
unique
0 on the
opportunity.
clock.
So one more question, please.
Okay.
This is Reza from University of Brussels.
Hi.
How these systems work when you have simultaneous events? Can you decode them?
Yeah, so we found in our training data set that many people for the hugging robot were squeezing and patting, so doing two things at once. And so we trained, our classifier had a special different, when we were already in, there was a state machine that when we were already in a squeezing state, which was very simple, I know, good old-fashioned engineering, then we could still detect pats and rubs. In this case, it didn't matter where they're happening because they can happen anywhere. When the skin has local receptive fields, what we typically do is we're processing in parallel. I have a paper under review now with my PhD student, Rachel Burns, who recently graduated, where we put tactile sensors all over the now and have people tapping it and touching it and petting it all over its body. And I think it's really important that we can feel multiple events. We should not make an assumption of single point contact. And that's, again, something, but this is something that computer vision can really help us by looking at by doing, say, a network that's just looking at the local areas, we can detect events in different places across the body.
Thank you.
Am I allowed to go now? Have fun.